Hi everyone. Today I will be talking about P1 in AQA GCSE physics. It's based on conservation and dissipation of energy. And the first thing I will start with is the energy stores and energy transfers. Now it's very important to have a look at the expectations from AQA. I have at this point the triple and double expectations of the first thing I'll be talking about. And here is the entry level expectations. And I also made a list of targets and expectations to outcomes for each target below here. Now, from looking at the actual specification, it says a system is an object or group of objects. That's very important when it comes to defining conservation of energy in a bit. So, for example, a system could be a ball thrown up and down in a vacuum. So that's the ball itself is the system. If the ball is thrown in normal air, then this ball and the air will be part of the system. So we'll look at this in more detail as we go through it. But you do need to know what a system is for double and triple physics. Please do make a note of that definition. Now, in the specification for double and triple, it says that you have there are changes in the way energy is stored when a system changes, and you should be able to describe all the energy changes involved. Also, you should be able to calculate the changes in energy, which we'll get to in a minute. And you should know the way that energy gets transferred. Now, I kind of simplified this in the outcomes section, the targeted outcomes. Very important to pay attention to certain things. So describe some example of energy stores. This is what we will be talking about. State the processes by which energy gets transferred. That's the other thing we'll look at right now. And we're going to look at examples and questions how we can apply this. To begin with, let's start with what is energy. Now, energy is the ability of something to do work, meaning if there was no energy somewhere, then there will be no ability to do anything. There will be no ability to do work. We can measure energy in different energy stores using calculations, which we will get to through this video. But in general, if you feel a bit stuck about what energy is, if we didn't have energy in our bodies, we wouldn't be able to get out of bed. It will feel like an exhaustion if you want to simplify it in those terms. But you need to know the definition that's given here as the ability of something, an object or a person to do work. To continue, we're going to have a look at all the different energy stores. So I made a list of all the energy stores that you do need to know. This doesn't go for the entry level. For the entry level, you need to know up to this point, and I will talk about it. So the energy store, the chemical energy store of an object is energy stored between chemical bonds of substances. So car fuel like petrol, diesel, it stores energy within its bonds, so a chemical reaction will release that amount of energy. Food, so food has sugars in it, and sugars are needed by our body to respire, so a process called respiration, which our body releases energy with. Batteries, the same thing, they release energy through chemical reactions. Wood, the same thing, so a piece of wood just sitting there will have nothing at all. It will look like it has no energy, but in reality, if I heat it, so if I alter the chemical bonds within the wood, it will start burning and releasing energy. And hot packs as well work the same way for those people that are into sports. Now, we said food is one of the objects that have a chemical energy store. Kinetic energy, every object that is moving has kinetic energy store. So a car driving, a person walking, a trolley being pushed, all of those are examples. Gravitational potential store is when the energy stored in an object that is raised above the ground. So in general, if we look at this picture here, I have the normal level ground. So let's say that the ground is here, the plane is above the ground, hence the object has energy in its gravitational potential store. At the bottom, we assume that objects at ground level have zero energy, and as they lifted higher up, the gravitational potential energy increases. This is the energy stored in objects due to their position relative to the ground. Going back, we have the elastic potential store. Now, this is energy stored in an object when it is squashed or stretched. So, for example, if I'm using my own energy to stretch a hairband, then I'm storing that energy in the hairband. If I'm squashing a sponge, the same thing, I am using my energy to squash the object. So I'm applying a force to squash it, and hence what we see as elastic potential energy. Then thermal energy is energy stored in an object due to its temperature. So for example, if I had a cup of coffee and a cup of water, obviously the cup of coffee will have a much higher temperature than water, and hence the cup of coffee will have a greater energy in its thermal store. Then going to the other three energy stores, which are not directly mentioned in the specification, but you should know about them. Nuclear energy is the energy stored by the nucleus of atoms. So the atoms, as you already know, have a positive nucleus and negative electrons spinning around them. So we'll just label this as positive nuclei and positive protons inside the nucleus. Now the idea is that these protons in reality shouldn't be close to each other, because positive and positive charges repel, or negative and negative charges repel. But in this case we have positive, meaning if they're repelling, they're pushing each other away. Now, there is something that's holding them together, obviously, otherwise we would not have the structures that we have, we wouldn't be us as well. And the fact that they are being held by something close together, which is a strong nuclear force, which you do not need to know about that right now, is one of the strongest forces in the universe. But the idea is that since something is holding them together, that means there's a lot of energy holding them together. And if they break apart, if the nucleus breaks, it releases that energy. And that's what they use in nuclear power stations through fission process, which you will learn about later on in other topics. So nuclear energy, like we said, is energy stored in the nucleus of atoms. Now, this also happens in fusion in the sun, when you have smaller nuclei joining together, or fission in power stations. This is a good point to remember, that it could be a synoptic link towards this as well. And then you have electrostatic energy store. This is the energy due to attractive or repulsive forces between two charged particles or objects. So if I want to push the same charges, so positive and positive charges together, then I will have to use energy to push them as close together as possible, because they're repelling, they're the same charge. Or if I want to pull the opposite charges apart, so a positive and a negative charge or object apart from each other, then I'll have to use energy. That's what we mean by energy in that store. And then we have magnetic. So this is an energy due to attractive or repulsive forces between two magnetic poles. So you are used to magnets and how they feel, how they behave. So you have the North Pole and the South Pole. They're actually attractive, so that means that they will pull each other towards each other. And that will mean that if I want to pull them apart, I have to use my own energy, and that energy is stored as magnetic energy store. This topic is very important in terms of its wording, and I will I will have a look at some exam questions as well, or practice questions for you to go through and understand as well. But these are the main energy stores. Now, how can energy be transferred from one store to another? Well, it can happen in 4 different ways. It can happen mechanically, meaning that you need a force that acts on the body for energy to be transferred. So you have to be moving an object through a distance using a force. Now, a force, just a very quick reminder here, a force is simply a pull or push. There's nothing fancier than that. It's just simply a push or a pull. So every time we push or pull something, we are transferring energy. Every time we lift an object off the ground, we're pulling it upwards. So we are transferring energy from our chemical store to the object's gravitational potential store. This is the wording that we will be focusing on, because these energy stores are the object's energy, basically, and we'll look at it in more detail. Then you have another way of transferring energy is electrically. So instead of electricity can transfer energy from a power source, I don't really like that word. Let's call it the electric current or the electric charges transfer energy. For those of you that I do teach, we did see electrons in a wire, and we said that the electrons are the charges, obviously, in a wire that carry the energy from one place to the other. So if I have a battery connected to a light bulb, and many of you will have already seen these electrical circuit diagrams. So I have electrons everywhere along the wire. They're already there. The battery provides chemical energy store. So all the chemical energy store of the battery gives the energy to each electron, and then the electron carries that energy to the light bulb, and the light bulb lights up. We'll look at it in a bit more depth later. So electrical charges can transfer energy from one place to the other, from one store to another. Heating is another way of transferring energy from one store to another. So thermal energy can be transferred by conduction, convection, and thermal radiation, which we will discuss more in P2. And then you have radiation. In this case, it's radiation / waves, because light and sound, so sound is not radiation, it's a wave, they can carry energy from one place to the other. So that's what carries energy from one store to the other as well. I wanted to start with some examples, so let's start now. So one of the examples mentioned in the specification is for you to be able to explain and describe the energy stores changes and energy transfers or processes in which energy is transferred throughout. It's very important to keep these key terms: energy stores, energy transfers, or energy processes, which means the same thing as energy transfers. So the first one is an object projected upwards. So in this example, I just simply have a ball. So I need to know what happens when to the energy stores and energy processes involved in this case. So what I have is the ball being thrown upwards. So it's moving, it's gaining energy in this kinetic store mechanically, because obviously to throw a ball upwards you need a pull or a push force. And once it reaches its maximum point, so in this process we had kinetic energy as it was rising, so energy being stored in the kinetic energy store of the ball. But when it reaches the top point, where it momentarily stops at this point, all the energy gets transferred mechanically to the gravitational potential store of the ball. Obviously, we are ignoring air resistance in this example, but for those of you who are targeting for something like greater than a 6 or 7, you need to also be able to describe other energy transfers taking place. So as the ball is moving upwards, it's experiencing air resistance. So you have a lot of, it collides with a lot of air particles that are around. So we can't see them, but objects, including ourselves, collide with so many air particles, and each collision is like a hit, basically, so a push. So a lot of the energy goes to overcome those pushes. So if you start clapping your hands for a long time together, you will notice the heat up. So a lot of times energy gets transferred to the thermal store of the object and the surrounding as well, due to air resistance or even friction between objects. If you rub your hands together, you will feel them heat up. That's because of friction between your hands, which means that energy is being transferred from the kinetic store of your hands to the thermal store of your hands and of the surroundings, as the surroundings also get heated a little bit. Another example mentioned in the specification is for you to be able to describe the energy transfers and stores taking place when a moving object hits an obstacle. So if the object is moving, it has energy in its kinetic store. The force is given by the engine, obviously, to move forward. So if it collides with a non-moving object, then all the kinetic energy, all the energy in the kinetic store of the car now gets transferred to the thermal store of the car and the object it collided with, as well as the thermal store of the surroundings. That's if you, like I said before, if you clap your hands together, you'll notice how hot they get eventually, or even if you bounce a ball on the ground a number of times, you will also notice how it warms up. And that means that the thermal store of the object has increased, and the kinetic store, obviously since it's no longer moving, has the energy in the kinetic store of the object is zero if it stopped moving after it collided. So all the energy from the kinetic store of the object gets transferred to the thermal store of the object that was moving, that it collided with, and to the surroundings. Eventually it will dissipate to the surroundings. And the next example is a vehicle being accelerated by constant force. So in this case, just stop the crash from happening again. So if the vehicle is moving, so in this case the car, the energy from the chemical store of the car, so the fuel, otherwise the car wouldn't be able to move, is being transferred to the kinetic store of the object through a force, so mechanically, because obviously the engine is applying a force on the engine. But in a different situation, if we consider the other effects, not all the energy from the chemical store of the object actually goes to the kinetic energy store, because once again you have air particles all around, and so assume that these are all air particles. We're not supposed to be able to see them, but for the sake of explanation here, I'll draw it like that. So as the car is passing through air particles, it collides with them, so it hits them, so they are applying a force against the car. And also friction between the car and the road creates also a lot of causes a lot of the energy not to be fully transferred to the kinetic store, but to be also transferred to the thermal store of the car, the surroundings, and the road as well. A simple model though of this, a simple energy transfer diagram would say that the chemical store of the car gets transferred to the kinetic store of the car. The rest of it is a bit more for those who can develop their answers better. And another example is a vehicle slowing down. So where is all that kinetic energy, for example, going? So I have my vehicle again. It's got energy in its kinetic store, and as it applies the brakes, the brakes cause friction on the metal plate that's spinning between them, and that energy is being transferred to the thermal store of the brakes, the car, and the surroundings to slow it down, to stop it from moving. Another example is bringing water to boil in an electric kettle. Now, an electric kettle works by heating it up through the power supply that is connected to, so through the plug. that means that we're transferring energy electrically through an electric current to the heater inside the kettle. So you have a heater inside of it that heats up the rest of the water. If you have a look inside the heater, you'll see this heating element inside of it. So the electric current causes the heater to heat up, and that increases the energy in the thermal store of the water, but also the thermal store of the container of the actual kettle, plastic or metal around it, and the thermal store of the surroundings. That was the examples mentioned here, but I will also give you more example questions. Okay, so this is an example of a bungee jump. Usually these kind of questions that give you the words missing will be found in foundation papers, and if there's missing gap questions in higher paper, they will usually not give you the words to figure out. So we see a student that's connected to a bungee cord, and before he jumps, obviously he's above the river by a huge distance of 20 meters. Well, the cord has 20 meters, so obviously he's longer than that. Then it says the student jumps off the bridge. Complete the sentences to describe the energy transfers. Before the student jumps, so this is before, this is keyword, so we need to complete the sentences. Jumps from the bridge, he has a store of. So if he's all the way up there and he's not moving yet, so before he even jumped, according to what we already know, if he's higher position than the ground level, then that means he has energy in his gravitational or her gravitational potential store. When he's, then it's him. When he's falling, so while he's falling, the student's store of what type of energy increases. So as he's falling, he's moving, right? If he's moving, then the student has kinetic energy store, has energy in his kinetic store. So that's the one that increases the kinetic energy. And when the bungee cord is stretched, now we have a material that can stretch, the cord stores energy. So you can see it's not talking about the student's energy store. It's talking about the actual cord, because that's where the energy gets stored in. So the cord stores energy as elastic potential. I'm just writing them in abbreviations very quickly. Now the next question, once again, a foundation type question. Says figure 1 shows appliances attached to the house. A coal-fired power station supplies electricity to the house. A coal-fired power station is simply a fossil fuel power station, so they burn coal to release energy from it. Remember, that's a chemical energy store. Give the names of the useful energy stores using words from the box. I will also go into useful in a bit, the meaning of it, but I think it's quite easy to understand. Now, each word may be used once, more than once, or not at all. So these are key things to pay attention to. A lot of times I get questions like, oh, can I use this word again? Or can I, not use it at all? So be very careful what the question asks. It usually gives you clear guidance. So a gas boiler transfers energy from a... Now, in this case, I already identified before that is a coal-powered fire station. So coal has a chemical store. So a boiler transfers energy from a chemical. So a boiler's job is to do what? It's to heat the house. So it gets the energy from the chemical store to the thermal store. That's the useful. So this is the useful energy stores that we're interested to mention here. Now there's another example. This is in terms of the shower. So as water flows from the shower, energy is transferred from so the water is high up. So if the water is high up, that means it's from in the gravitational potential store of the water to a kinetic energy store of the water. A ceiling fan transfers. So now we're going to the third example in the house. since the fan is supplied electricity from a coal-fired power station, again, the energy store is chemical, so from a chemical store, since it uses electricity, which is provided by a coal-fired power station. Two of the power station, if the fan is spinning, that means it's moving, so to the kinetic store of the air. Then I'm gonna go to so these are more of foundation double questions, and then this is one from 2018 paper. This is not the whole question, but it's part of a question. It says it shows a mobile phone being recharged by a portable power source. Why does the battery in the phone need recharging? So it says tick one of the box, so only one. If you tick more, you will not receive any marks. So the store of a chemical energy in the battery has reduced. The store of thermal energy in the battery has reduced. Is that why I would charge my phone? I will recharge my phone due to the thermal energy? Not really. I don't want my phone to be hot. It actually wastes energy. The store of kinetic energy in the battery. I know that my battery can't move and recharge itself, so that's not true either. And the store of gravitational potential, once again, this is due to position, so that's not true. Now this is application of what we've talked about, the energy stores. In this case, obviously, we know that batteries have chemicals inside of them. That's why we recharge our batteries, so it's the first one. Then there's another question from the Triple Foundation paper of 2018. It says, complete the sentences, choose answers from the box. It doesn't tell you can use it once, more than once, or not. This is because it's Triple Foundation, I guess. It shows you a cyclist riding along a flat road, and it says to complete the sentences by choosing the answers from the box. So as the cyclist accelerates, the something energy store in the cyclist's body decreases. It's very, very important. So what energy store inside the cyclist's body decreases as he's cycling? Because he is accelerating, he's moving faster and faster, which should mean that he has kinetic energy, and that increases as he's speeding up. So we know that indeed he's not moving up or down, so it's not gravitational potential. If we go by the elimination method, and we know that he's not really squashing or stretching, so it's not elastic potential. But it does make sense that since our food are chemical stores of energy, so are we when we eat it until it gets released. So from the chemical, so as he's cycling, he has less and less energy from his food, because obviously he's using it within the bicycle to ride the bicycle. And the something energy of the cyclist increases. So which part of the cyclist increases? This is kinetic energy. Now for the triple higher, it's exactly the same question, but instead of giving you any words, it doesn't. And there is a bit of a difference, which I'll go into in now. So you see the same question, but obviously there are differences. It says, shows the cyclist riding along a straight level road at a constant speed. In this case, he's not accelerating. So as the cyclist rides along the road, the something energy store in the cyclist's body decreases. This is the similar part with before, is the chemical. So every time we exercise, the chemical energy store in our bodies decreases, and other energy stores increase as we transfer energy from one form to the other. And I will go into that in a second as well. So the speed of the cyclist is constant when the work done by the cyclist is something the work done against air resistance. Now, for someone to have the same speed, the work done to overcome air resistance, if you're going at the same speed, needs to be equal. So the cyclist is equal to or the same as the work done against air resistance. So this is why this is in a higher paper, because it's a bit more of an application concept. At this point, it's a good point to mention conservation of energy is very important. Conservation laws always exist, and they're quite similar as well. So conservation of energy states that energy cannot be created or destroyed, meaning I can't just make energy out of nothing. If I don't eat, then I will eventually get too exhausted, too tired, and then obviously, death will follow. But I cannot create energy out of nothing. I can't just say I'm breathing in air and that's what's going to give me energy. That's not enough. It cannot be destroyed, so it can only be transferred between one energy store to another. So it can be only transferred. So the net energy in a system, the net change in energy in a system is zero at any point in time. Now this is the outcomes again in terms of targets that you should expect to know. If you're targeting for grade 4, then you should be able to state the conservation of energy and state what a closed system is, which we saw before. If you have a target of 5 to 7, then you should be able to apply the law, and we'll see some example questions at the end. It's a bit hard to unpick the questions in this topic, but you will see in a bit. At least keep in mind or make a list of the outcomes that you do need to know in terms of these topics to help you with your revision. And you should also be able to describe the energy changes, explaining why objects stop oscillating or bouncing eventually. For that, I will do a quick description as well now. Now, if you want a higher target of an 8 or a 9, then you should be able to explain why forces cause heating effects. Is what we said before already. If you are heating an object constantly, eventually the particles within the object will start moving faster, it will start heating up. You cause more of the vibrations to go to the object's particles or atoms and molecules that make it up. And you should also be able to link this to the conservation of energy. Once again, it's a bit hard to do without an exam question. And usually exam questions have a lot of parts that are linked together. So we will have a look at it at the end. And to describe how energy distributed in a closed system, and to explain all the energy changes. Once again, these can only be seen easily in application. So what I will just do is focus a bit on this part, the describing the energy changes in energy stores, explaining why objects stop oscillating or bouncing eventually. And the most common example that I can talk about is when you're bouncing a ball, to begin with. If I have a ball and I drop it from a height and it starts bouncing, eventually it will reach a point where it will stop bouncing. And we know there's a lot of energy transfers taking place in this point. So to begin with, it has gravitational potential energy. As it falls, it changes to kinetic, collides with the ground here, and a lot of the energy gets transferred to the thermal store. Some of the energy actually gets transferred to the thermal store of the ball and the surroundings. And the ball continues, transfers energy to its kinetic store, then again to the gravitational potential, then the energy goes to the kinetic store while it decreases in the gravitational potential store of the ball, and this continues until it eventually stops bouncing. Now, it would have bounced forever at the same height if there was no air resistance and if we could ignore the heat effect, thermal effect of the collision between the ball and the ground. But the fact that some of the energy is wasted as heat in different parts, so when it collides here and with the air particles as well, when the ball collides with air particles, some of the gravitational potential, the energy in the gravitational potential store, the beginning, if we consider it actually from the very beginning, if it had, for example, 1,000 joules of energy while it was there, that 1,000 joules of energy doesn't just disappear, it actually dissipates to the environment, to the surroundings eventually. So what you have is this energy changing fully as the ball falls, to kinetic. So at this point, you will still have 1,000 joules in the kinetic store of the ball, of energy in the kinetic store of the ball. But as soon as it collides with the floor, there's some heating effect, and that means some of the energy now that the ball originally had has been redistributed to the thermal store of the ball and the surroundings. So if we assume that here 100 joules went towards the thermal store of the surroundings, that means the ball only has 900 joules of kinetic energy as it rises, and hence here it will be 900 joules, which means it will keep reaching lower and lower height at each time it collides with the floor, and more energy, and the air as well, so with air resistance. So friction and air resistance cause energy to be redistributed to the thermal store of the ball and the surroundings until eventually the ball stops moving. So as a general rule, energy transfers to the thermal energy store of the surroundings and the object due to friction and air resistance in this case. Now we're going to have a calculation. The first equation that we're going to have a look at in this topic is how to calculate energy transferred by a force. So you can see from the outcomes of the targets, so you should be able to state that energy is measured in joules, just like we measure distance in meters, or we measure time in seconds, and current in amps, and so on. Energy is measured in joules. Very important to remember the unit, and to remember that it's written as a capital J, not a lowercase j, please. So the word is joules, but the symbol is J. We always write it in the symbol of the unit. You should be able to calculate the work done by a force in a simple way. So usually you should remember this equation. Actually, you should be able to recall the equation for work done, and I will show it as well. You should be able to describe the effects of frictional forces on objects, which we already have discussed. You should be able to rearrange. So if you want to get a higher target, you should be able to rearrange the work done equation, which I will show you, to calculate the two variables that affect it, and explain how work done overcomes frictional forces in different situations. So we have seen this in one of the questions, in the higher triple paper question a while ago. And to apply the equation of work done in a wide range of contents. And that's because you will have questions that involve substituting quantities in each other. So that's what that means. So usually it will be substitution question that, or in general, not directly telling you how to calculate or what to calculate. You might be more responsible for that. So firstly, we said work done is energy is the ability of something to do work. So the first thing that I will make sure that I mention is what we mean by energy transferred. So every time we say energy transferred, or if I want to calculate the energy transferred, I'm also calculating the work done, which means exactly the same thing. Every time I say work done, I mean energy transferred. Every time I say energy transferred, I mean work done. Is exactly the same thing. Now, the energy transferred always depends if it's mechanically transferred, very important. It was one of the processes that transfer energy. So if the energy is transferred mechanically through a force, then the work done, or the energy transferred, like we said, it means the same thing, is equal to the force that I'm applying on the object times the distance moved in the direction, very important, in the direction of the force. So the energy transferred mechanically only relies on the force I apply and the distance I move the object. So for example, if I have a box and I'm pulling it, remember we said I'm applying a force, then it's a pull, or a pull is a force. So if I'm pulling it and the box moves over a specific distance in the same direction as the force, so you can see the force is parallel, so parallel to the distance moved, then I can calculate how much energy I transferred to the box to move it. work done, as we said, is the same thing as energy transferred, and the unit of energy transferred is joules. The unit of force is newtons, and the distance moved is measured in meters. If you have millimeters, centimeters, or even kilometers, you need to convert them to meters. I will show it when I go through exam questions. Force should be always measured in newtons, nothing else, and work done always in joules, if I'm going to use it in this equation. I will also write this down in symbols, the equation, so I can make it easier. So work done can be represented by symbol E for energy, or energy transferred. Force always gets represented by capital F, and usually distance with a lowercase d, but you also see it as an S. So I'll leave it as an S actually for this case. So we have the equation written down. I'll also draw the triangle for those of you who feel more comfortable rearranging this type of equations. So you have force, distance, S, and the energy at the top. So if I want to calculate energy, I cover E, and this means times, this means divide, this line between. So if I want to calculate energy, then it's force times distance. If I want to calculate force, then it's energy divided by distance. If I want to calculate distance, I cover S, and it's energy divided by force. So make sure that you get the grasp of that if you are unsure of it. So usually we'll have questions like this, and every time you read a question, remember, it's like a mystery that you have to solve. That's what questions asking you to solve something. And usually mysteries, like if you're a detective, then they involve you finding clues, and the question itself has a lot of clues within it. So I will start by highlighting them or underlining them and labeling them. So the student pushes a box with a force of 50 newtons. So he's pushing it, that means he's applying a force of 50 newtons. That's my force. And it's in newtons, so I don't need to change the units. Across a distance of 2 meters. So that's my distance that I don't need to change because it's in meters as well. I don't need to convert the units. How much work did the student do? So I need to calculate how much work he's done. And I know that work is the same thing as energy transfer or work done. So this is what I'm calculating. So I'll put a question mark there. It's easier if you make a list of these values. I'm just going to do it here for you now. So force is 50 newtons. Distance is 2 meters. And work done is what you need to calculate, or the energy transferred. Now I know that since it's the energy that I need to calculate, it's straightforward since my equation is like this. And I just simply put the numbers in. So 50 goes there and 2 goes there. So that's equal to 50 times, so whatever number is next to the symbol I used will go in its place and we'll replace it. So we have times 2, which gives me 100. And I know energy is measured in joules, so it's 100 joules. That's a simple example. Some questions might ask you to rearrange, so I will show you how to rearrange here. So if you had to calculate the force instead of the energy, then you have the equation E is equal to F times S. Now it's much better if you are targeting to get something higher than a 5 in your exams, then you should be able to rearrange, and I will suggest that you learn the symbols instead of remembering the whole equation. In that way, obviously, if you learn the symbols, you will remember the whole equation. And it's much easier to work with symbols rather than the full word. So work done, force times distance. You don't have to rewrite it if you know the symbols for it. So if I want to rearrange to calculate force, then I need to make force the subject of the formula. That means I need to get rid of the distance from next to it. Since I'm timesing it, I need to do the reverse action. And you know, times and division are reverse actions to each other. So instead of timesing now, I will divide, and I need to do it to both sides because this is an equal sign between them. So whatever I do to one side, I do to the other side. And then you have divide both sides by the distance. Now, distance divided by distance is 1. 5 divided by 5 is 1. 2 divided by 2 is 1. So it's like saying force times 1, which is just force. And then, therefore, force is equal to the energy transferred or work done divided by distance. Alternatively, you can use the triangle up here. Is your choice. And if you want to calculate distance instead of force, then you do exactly the same thing. By instead of getting rid of the distance, you're getting rid of the force. Once again, since you're multiplying it, you can divide both sides by the force, and hence you end up with, so force divided by force is 1. You end up with energy divided by the force. So the next bit I will look at with you is the other calculations that you will need to know. Like I did mention before, energy stores can be calculated. Most of them you'll be able to calculate, not all of them, but most of them by the end of the course. We looked at already one equation. Now these are the 3 equations that you will need to know. You should be able to calculate the amount of energy associated with a moving object, meaning the kinetic energy store of an object. A stretched spring, so in other words, elastic potential energy store of an object, and an object raised above ground level, which is the gravitational potential energy store of an object. So you will need to be able to recall 2 of these equations, and the third one is given to you. The ones that are that you will need to recall is the kinetic energy and the gravitational potential energy store. The elastic potential energy store will be given to you, but that does not mean you should not be aware of what it is and how you can calculate it. Also, I have given you a list of the outcomes for different targets. Once again, state is simple things that you can do for targets 1 to 4 is to just state what can affect the gravitational potential energy store of a system. Now, if we look at the equation for gravitational potential energy store, it tells you that the gravitational potential energy is equal to the mass times the gravitational field times the height. Now, gravitational field strength is something that's constant, is the same whether you standing, well, it's assumed to be same on Earth everywhere you are, and even if you go to a bit of a higher height, it will still be the same. For the purposes of gravitational field strength in terms of Earth, that value for AQA is equal to 9.8 newtons per kilogram. Now, gravitational field strength is how strongly a planet is actually pulling us. For example, if we went to the moon will have a lower gravitational field strength because it's smaller, it doesn't pull us as much. I will do another video on this topic later when we have to cover the content for it as well. So in other words, I can write the gravitational potential in terms of symbols. So gravitational potential energy can be given by symbol EP. The mass, which is equal to mass, mass is always written as a symbol M, times the gravitational field strength, which is just G, times the change in height, in other words, or height. So if it's if it starts at 0, the height from ground level, then obviously is how much it changes. But usually it's the change in the gravitational, in the height. Now, energy, we said, is measured in joules. So gravitational potential, elastic, kinetic, thermal, they're all measured in joules. Mass is measured in kilograms, always, not in grams. Gravitational field strength is newtons per kilogram. We'll come across it again soon. And height, always in meters. Any other units need to be converted in if you were given millimeters, then you need to change it to meters and so on. Now, you should be able to recall this equation, but also at the same time, you do not need to know this exact equation if you're doing a double or foundation paper. You could be given this equation as weight times height, and I will explain that in a bit. Now, you should be able to recall this and easily calculate gravitational potential energy if you're given the mass, gravitational field strength, and height, or if you're given the weight of an object and the height. This is a good point for me to talk about weight here and mass. Now, mass of an object and weight of an object are different things. When we say I weigh this much, I weigh 50, 60, 70 kilograms. Now, that's not your weight, that's your mass. This is the amount of matter that you're made from. Your weight is how strongly the Earth is pulling that mass. So you have to multiply it. So weight is equal to mass times the gravitational field strength. So in other words, weight is equal to m times g in terms of symbols. Weight is a force, it's in newtons. Mass is in kilograms, and then newtons per kilogram. Now, if I want to calculate the gravitational potential energy using weight instead of mass times gravitational field strength, so we already saw that gravitational potential energy is mgh. So mass times gravitational field strength times height. Now, in this case, I'm replacing mg by weight times the height. So for target grades 1 to 4, so mostly foundation papers will require you to do this simple calculation, and you should be able to recall that. Now, for targets that are higher, you should be able to describe how different gravitational field strength affects the gravitational potential store of a system. So I already mentioned before that the gravitational field strength on Earth is 9.8 newtons per kilogram. On the moon is 1.6 newtons per kilogram. That's because the moon is much smaller than the Earth, so it has less mass, so it has less pull towards us. Now, every object that has mass is attracting other masses, meaning I did mention before magnets, how the North Pole and South Pole attract, whereas the South and South or North and North repel. Those are pull or pulse forces. Masses always attract each other, they don't repel, so they're always pulling each other towards each other, pulling towards each other. So that's a force. That means that the Earth is pulling us to its surface much stronger than the moon does. And this is what it wants you to be able to explain. And since we know that gravitational potential energy relies only on these three quantities, then if I increase the gravitational potential or decrease it, if I increase or decrease it, that would directly affect, for the same mass object and for the same height of moving it, obviously, then my gravitational potential energy will either increase if I have a higher gravitational field strength, or decrease if it's less. You can use numbers to figure that out as well. You can put the numbers in for 1 kilogram of mass and 1 meter of height, for example. You'll see straight away the difference. And you should be able to calculate in terms of here using this equation. If you want to get higher target grades, then you should be able to rearrange this equation and apply it in a lot of different contexts. And I will show you how that happens when we do exam questions in a second. You should also be able to explain all the energy changes during a fall or height increase to account for any heating effects. For example, bungee jumping is one of the best examples to have a look at as well. Then it's quite similar for kinetic energy and elastic potential energy. So you should know for targets 1 to 4, you should be able to state what factors affect elastic potential and kinetic energy. You should be able to calculate for high targets. And for the top target grades, you should be able to rearrange these equations in different contexts that you're given. A lot of this involves substitution, rearranging, equating equations together that depend on the question's content, and I will show you at the end of this part. So what factors affect kinetic energy and elastic potential energy, and how can we calculate them? Now, if you look at the equation for kinetic energy, you see that it's a half times the mass times the speed squared. This is a common thing that many people leave out of the question, the squared part, and they tend to lose all of their marks. You need to be able to recall this equation, so remembering and memorizing it. I always notice how many people make mistakes here just because they forget to square it and hence lose all of their marks. You need to start showing your equations that you're using to avoid missing out the mark if you forget to put the square at the end. So once again, kinetic energy is energy, so it's measured in joules, mass is measured in kilograms, and speed is meters per second. You should be able to convert units once again. And since we know the equation, we also know what can affect kinetic energy. So if I increase the mass of an object, that will mean that it will increase my kinetic energy. If I increase my speed, then that will mean it will increase my kinetic energy. So mass and speed affect how much kinetic energy an object has. Going to the next equation, elastic potential energy is a half times the spring constant times extension squared. Once again, this is given to you, and many people tend to forget this squared part, so they end up losing all of their marks. All you're required to do for lower grades, usually, if you have a target grade of a lower grade, then you're just expected to simply figure out what quantities you're given in the question and plug them in the equation. You should be able to use the formula worksheet that you're given in the exam to pick out this equation from it. You don't have to memorize this one, but you do need to memorize the other two. So once again, we can see that elastic potential energy is affected by the spring constant and the extension of the spring. Now, the spring constant is how stiff a spring is. If I can stretch the spring easily, then it will have a low spring constant. If it requires a lot of pull from both ends to extend it, then it means that it has a high spring constant. So the higher the spring constant, the stiffer a spring is. And extension is how much it extends by from its original length. So that's another quantity that you will see popping up when we do Hooke's law again. Here I'm going to use the symbols to show you how you can rewrite the equations in triangles for lower target grades, for those of you who are struggling to rearrange. And I will also show you how you can rearrange it. Now we're adding 3 columns at the bottom for the gravitational potential energy. When it comes to kinetic energy and the elastic, it gets a bit more difficult. You can leave it as 0.5 v squared, so that's a v for I didn't mention the symbols before, but you can see the symbols here below them on the side. So that's the symbol equation instead of word equations. Please do use them to make your life easier. It's easier to learn the symbols because it's quite straightforward when it comes to equations in physics. And then you have the elastic potential energy, which is a half k squared. Now, if I want to rearrange, this is quite similar to the rearrangement I showed you before. But if you do want to rearrange for these equations, for example, to calculate velocity, I will show you how to do that. Once again, high grade people are expected to be able to get these questions right, but you will not lose out anything if you do a bit more practice. So just pause the video, rewind, rewatch, repractice. It's always a good practice to have. So we have this equation. Now, if a question is asking me to calculate velocity, then I'll need to make the velocity the subject of the formula, but the velocity is also squared, so I will need to take that into account. So firstly, I will leave velocity on its own on this side. That means I need to get rid of a half m from it. Now that's a half times mass times velocity squared, which means I can divide both sides by half m. Now half m divided by half m is 1, so that can go. And we have the kinetic energy. Now, if I have something as 1 over 1 over 2, that can be rewritten as 1 times 2 over 1. So I'm inverting the denominator fraction and multiplying it by that. And if you do that on your calculator, if you do 1 divided by 0.5, you will actually get 2. So you can try that. It's your choice. So then that will be 2. Oh, that will be 2, sorry. And that will be divided by m is equal to v squared. Now I'll rewrite it to make v squared on this side so it looks nicer. It's the same thing, they're still equal, just flip the sides that they're at in relation to the equal sign. And then since I have squared there, I need to, the inverse of squared is square rooting both sides. Now square root actually means to the power of a half. 2 times the power of a half is 1, so that means v. So this cancels with the square root, and then you're left with square root of 2 times kinetic energy over mass. That's one way of rearranging this. The same thing applies to this equation. You have the elastic potential energy is equal to a half times spring constant times extension squared. And if I want to find the extension, I rearrange, so I get rid of a half and k. So since they're multiplied, I do the reverse function. I divide both sides by that. That leaves me with 2 E over k is equal to e squared, because these cancel. And then you square root both sides, and you have e is equal to square root of 2 e over k. So you should be able to do these activities easily. Now here I have a foundation exam question. It shows a girl skateboarding on a semicircular ramp. Now in the diagram, like I said, we need to look for the clues. We need to look for the values that it gives us and list them and label them. Now in the diagram you can see there's the height of the ramp given to you. It also tells you the mass of the girl, which is 50 kilograms. So I'm given the height, I'm given the mass, and it says calculate the gravitational potential energy of the girl at the top of the ramp. Use the equation, so it even gives you the equation in this case, and it gives you the gravitational field strength, so G. You do have all of the quantities that you need. So you have the mass, you have G, and you have the height. So you just simply have to put the numbers in that you're given in the diagram. Now remember, we are interested in the height, not anywhere else, because that's the whole point of gravitational potential energy. So my gravitational potential energy will be 50 times 9.8 times 4, and you just put the numbers in the calculator and you get the value in joules. And it also is asking you to calculate the kinetic energy of the girl at the bottom of the ramp. It says the girl has a speed of 7 meters per second at the bottom of the ramp. You calculate the kinetic energy of the girl at the bottom of the ramp. So we already know that her mass is 50 kilograms and we know her speed now is 7. So all I have to do is just simply put my numbers in. 0.5 times 50 kilograms times the speed, which is 7, but it's squared, the speed. Just place that in the calculator and you should get your answers. So this is the question that I meant before about when they ask you questions, it will be all as a series of parts of the same question. It says not all of the gravitational potential energy has been transferred to kinetic energy. Which two statements explain why? Tick two boxes. So it says some energy is wasted. The mass of the girl is too low. Well, she's not losing mass while she's moving, so that doesn't count. So that's incorrect. The ramp is not high enough. That, once again, has nothing to do with the energy transfers. The gravitational potential energy of the girl is not zero. And the speed of the girl is not that great. So that's wrong, because that has nothing to do with not all the energy being transferred. Now, some energy is wasted. Remember, we said that through friction between the skateboard and the ramp, or air resistance, so that energy gets transferred to, some energy gets transferred to the thermal store of the surroundings. So some energy is wasted. That's true. And also the gravitational potential energy of the girl is actually not zero at that point, because you can see there is some height left. So if this is considered to be zero, the energy in the gravitational potential store is considered to be zero at this level, then obviously she's still higher up, so some gravitational potential energy is still present. Energy is still present in her gravitational potential store, sorry. Need to use the correct wording, very, very important. So these two are correct. And it does say which two statements, and explain why. Do not tick more than two boxes. If you do, you'll start losing marks. Marks get deducted for each extra tick that you have. So these equations are, questions, are once again a bit higher level. So question 3.3 here is for grades 5 to 7, and 3.5, question 3.5 is for grades 8 to 9, and I will explain. So question 3.3 says the gravitational potential energy of an object lifted 16 meters above the surface of the rocks. So we are given already the height. Just by reading the question, you're trying to find the clues. And it's telling you the gravitational potential energy, so it's telling you it's 320 joules. So already I have two quantities here. Calculate the mass, this is what I need to calculate, of the object. Gravitational field strength is given to you as this number. Usually if it's given to you, then you use the number that they give you for G. If they give you 9.8, you use 9.8. But usually I think for AQA, you have to remember it as 9.8 newtons per kilogram. So we know the energy, we know the height, we know G, and we need to calculate the mass. I know, and now I'm going to recall my equation. I'm like, okay, I know these quantities. I remember how they link together. Just recalling them. Is it good enough? Before I put any values in, I need to rearrange for M. So M needs to stay on its own so I can calculate it. And since it's multiplied by G and multiplied by H, I need to divide both sides by G and H. And that leaves me with the mass, which is the energy divided by G and H. I just simply put my numbers in, and I should get the answer. So that should be 2. So the mass is 2 kilograms. Says, the next part says, write down the equation that links speed, energy, and mass. Again, you should know that energy that's linked to speed. You can see that this equation doesn't have speed in there. Elastic potential energy doesn't have speed in it. So you should be able to straight away realize that that's the kinetic energy. Now remember, if you write symbols, then you have to name what each symbol stands for. So you might as well just write the whole thing together. Then it says calculate the velocity. Now this is when these questions get a bit harder. So you need to find the velocity. Now velocity is the same thing as speed. For those of you who already are taught, you should know that. So velocity refers to speed, so V, of the 2 kilogram mass. So that's the mass. just before it hits the rocks when it is dropped from a height of 16 meters above the surface of the rocks. Give the unit. So you are actually calculating velocity, which is speed. So the unit should be meters per second. I'll write that and get rid of that for now on. But then it's kind of linking three different things together. Well, two different types of energy. So you have the object, whatever object it is, lifted, the 2 kilograms object, at a height of 16 meters. And you need to find the velocity just before it hits the rocks. So you need to find its velocity right about here, so just about before it hits the rocks and stops moving. Now we know all of the energy that the object has here is in its gravitational potential store, but once it loses height, it all gets transferred to, and assuming that there is no air resistance, so no energy losses to the thermal store of the surroundings or the object, then we are assuming all the energy is being transferred to the kinetic store. And if I know the kinetic store, which the previous part hinted at, then I can easily now say, okay, since all of the gravitational potential energy went to the kinetic store, so here I had 320 joules of gravitational potential energy. Now all of that energy has gone to kinetic, since at this lowest point, the gravitational potential energy store of the object has 0 joules. I'm assuming that no energy got lost in the process of it falling, no thermal energy was lost. So my gravitational potential energy is equal to my kinetic energy, which is 320 joules. Now this is one way of doing it. I will explain the other method of doing it. So I know that 320 joules is equal to the half times mass times velocity squared. I showed you already how to rearrange it, so I'm going to just straight away do it in one go. So it's 2 times 320 divided by the mass, which is 2. So that will give me just the square root of 320, which is roughly 17.88 and so on. So that's roughly about 2 significant figures is enough, because the question gives us the values in 2 significant figures. So that's about 18 meters per second. Now, I could have done it this way, or you could also do it in a way that the gravitational potential energy equation is equal to the equation of kinetic energy. If I divide both sides by mass, because they both have mass, so I can get rid of that. They cancel out. This 1 is equal to 1. Then I have GH is equal to a half V squared. Now, I just want to find velocity, so simply multiply both sides by 2 to get rid of the half. So I have V squared is equal to 2GH, and hence square root of 2GH. And that's enough. And then you just put the values in, which is square root of 2 times 10 times, the distance was 16 meters. So there you go. You have 2 times 16, which is 30. 2 times 10 is 320. So you still get to the same answer, whichever way you prefer to do it. This is one of the most popular parts of energy transfers topics, because many people realize what the useful purpose of a machine is. So all machines have a purpose, and even though we want them to do a job, that doesn't mean that all the energy we give into them is being used for that purpose. So for example, in a washing machine, you want the washing machine to wash your clothes. You don't necessarily want the washing machine to vibrate. You don't want it to make noise. And you don't want the outside of the washing machine to heat up. You do want the clothes to reach a specific temperature. You do want them to spin around. So you do want the thermal store of the clothes to increase. You do want the kinetic energy store of the clothes to increase as the spinning, but you don't necessarily want the thermal store of the casing of the machine to heat up, to increase, and you don't want sound. You don't really sound doesn't wash your clothes, so that's not a purpose. That's not a useful energy transmission to have. So for the outcomes, again, you should be able to state what we mean by useful and wasted energy. So, for example, sound is a way that energy gets transferred away from the device. So that's wasted energy, because that's not really useful for us. So wasted energy means energy that is not usefully transferred. So it's not going to do anything that's useful for us. Useful energy, on the other hand, is the energy that's transferred usefully to where it is wanted to be transferred. For example, a fan in a room. Like if you have a fan, then the fan's job is to spin around and to create wind. Now, the kinetic energy is useful. The energy in the kinetic store of the fan is useful, but not the thermal energy store increase. So that can be considered as wasted energy. When we say that energy gets dissipated, it means it spreads out. So eventually, all useful energy will be transferred to the surroundings. It will get dissipated. It will lead to the surrounding getting warmer, and as it spreads more and more, the less and less useful it becomes. So this is quite an easy concept, and many people really enjoy this part. So you should be able to analyze energy transfers to identify useful and wasted energy transfers. That's a very important part, as to question always yourself. Okay, so what's the purpose of this machine? What do I want this machine to do? And if there's things that it's doing that you don't really want it to do, then that means they're wasted energy forms. You should also be able to describe energy dissipation and how this links to work done. Apply energy transfers and processes to a wide range of scenarios. Once again, this depends on content of the question. And you should also be able to apply what we mean by energy dissipation in different ways. I also have a second list here. I just added them all together in one. I thought it would be much easier to go through it. It says, describe the energy transfers in simple electrical devices are useful or wasted. So I put a light bulb there because that's one of the most easiest ones to relate to. What do we want from a light bulb? We want it to light up. So we want it to emit visible light radiation. So when we do touch a light bulb, though, you feel the light bulb getting hot. You feel it hot. That's not what you want a light bulb to do. You don't really turn on the light to get, a heating in the room. You light up the room for you to have light. So useful energy is, in terms of, in case of this light bulb, is light, and wasted energy is in the form of thermal store of the light bulb and the surroundings. Describe the processes that waste energy in electrical devices. Now, this is very important. The process that actually does waste energy in an electrical device is the resistance in the wires. Just like we saw friction being friction and air resistance causing thermal transfers. In this case, the resistance in wires, as the charges are moving, they're colliding a lot, and they're causing heat to be given out. Now, explain how electrical devices operate in terms of forces and electric current. We will come back to this in a later topic that we will have a look at, that will make more sense then, even including this part. This is kind of a synoptic link to what we will be learning in P4. So now we're going to have a look at efficiency. Now, you should be able to state what is meant by efficiency, or even the equation. Now, efficiency is how much useful energy you get out of a machine. And And also you should be able to state that nothing is more than 100% efficient. I will also explain it as part of high targets. You should be able to calculate the efficiency in simple scenarios. So if you're given certain quantities, you should be able to do it. I'll explain that. For higher targets, you should be able to do it easily. And for targets 8 to 9, so this is a higher tier expectation, is to describe how devices waste energy, and I'll go through that, and how you can increase their efficiency. And also you should be able to rearrange the efficiency equation, which I'll go through some examples for that too. Now, efficiency is equal to useful output energy, meaning how much energy I'm getting in terms of in joules by the device, so how much is transferred by the device as useful, that we've discussed before, divided by the input energy, meaning the total input I'm giving into the machine. So if I'm giving 100 joules into a light bulb, for example, now, and the light bulb only uses, for example, 60 joules of that as useful, as light, transfers that as light, then that means that 40 joules of the energy is left as heat. Remember, conservation of energy. If I'm giving 100 joules into a system, then I should be getting 100 joules out of the system as a total. But only 60 joules of that is useful. So that means that the efficiency of my light bulb is 60 joules of useful divided by 100 joules of total input that I gave into the bulb, and that leaves me with 6/10, which is 3/5, which is 60%. Now if I times that by 100, sorry. Now I could have left it as a number, which will leave me with 0.6. So you can see already that this is how we can easily calculate the efficiency. Now, why cannot something be 100% efficient, more than 100% efficient? Well, if you look at the equation again and at the diagram I drew, that if this light bulb was more than 100% efficient, that means I will be getting out of it more useful energy out of it than I'm putting in, which is against the conservation of energy law. We said that you cannot create or destroy energy. So whatever you put in, you simply get out. So if I'm getting more out than I'm putting in, that means that I'm creating energy somewhere, somehow, and that doesn't exist. That's impossible. Now, I'm going to quickly discuss the factors that can increase wasting of energy and how we can improve them. Now, wasted energy can be wasted in a few different ways. So it could be wasted due to friction. It can be wasted due to air resistance, electrical resistance that we just saw, and it can be wasted through noise, like the example I said regarding the washing machines. Now, how can I minimize this wasted energy? If I'm designing these machines and I want to sell them at a higher price because, more efficient machines are sold at much higher prices. So if I want to remove friction from a machine or from a device, I can just apply a lubricant. So lubricated, so oil or something oily. If I want to remove air resistance from a car, for example, or from wind turbines or things like that, then I should make a more streamlined shape. That's how you can, like when you design it, you can minimize the energy losses as heat. So all of these cause thermal energy losses. Well, thermal energy, losses, wasted energy basically. So streamline shapes usually minimize air resistance. If you're not sure what that means, just Google it quickly. Pause the video and Google it. And if I want to minimize electrical resistance, then I can use wires, for example, with lower resistance, lower electrical resistance. And if I want to remove noise, now you can actually tighten loose parts of the machine to minimize the vibrations. That's what causes noise. Vibrations cause noise. So tighten loose parts. So this is the other way of looking at it. Now you should be able to apply this in different contexts. It's straightforward. The biggest mistake that I see is that sometimes students don't realize what the question is generally asking. So hopefully we'll see some examples now. You should also be able to rearrange the efficiency equation if you want to get the top grades on this. Now this is the last part of P1 topic. Now power is the rate that of energy transferred. So in other words, is energy supplied per second. If I'm talking about something being more powerful, it means it's transferring more energy per second than another machine. It doesn't only work for machines, it also works for things that humans do. So I could say that one of you is more powerful than another based on how much energy you're transferring at a single second. So for example, if two students had the same exact mass and they were running up the same amount of steps and same height, basically, then the person who will achieve or come first in that competition would actually be more powerful because they're transferring the same amount of energy in the least amount of time possible. That means it makes them more powerful. So depending on the situation, you should be able to apply that. So power can be calculated. Is equal to the energy transfer divided by the time taken. A triangle to help you rearrange or calculate can be given as power. Now the symbol for power is P. Energy is E divided by T for the time. Power is measured in watts. The symbol is just a capital W. Energy transferred again in joules, and time taken in seconds. Make sure that you are very confident with these equations. And then you just simply put it in the triangle and you can rearrange it and calculate it. Now for lower target curves, you should be able to just state the unit of power. Don't confuse it with joules. Power is different from energy. Energy is the amount of work done, but power is how that work done is, how quick that work done is being transferred. In other words, you should be able to calculate the power of a device when you're given the quantities. So simple calculation by replacing the just substituting the numbers in. And for higher targets, you should be able to calculate by rearranging. So you should be able to rearrange this equation and calculate the efficiency of a device using power ratings. Sometimes you can be given power ratings and told, I'll show you the examples so I don't confuse you. So for higher targets, you should be able to substitute other equations into the power equation. That's a very nice question I will have at the end to show you, and apply and rearrange the efficiency equation in a wide range of scenarios. The one that we have saw before, including power. So what I will do now is just go through some examples and we will be nearly done. So this is a question about how lubricating the wheels of a skateboard can increase the speed of the girls. This is a question that we saw previously, and it's a continuation part of it. It says use ideas about energy in your explanation. So I have to explain. In this case, I don't just state. I have to explain why, what my answer would be. So if you lubricate the wheels, then what do you reduce in this way? If I'm lubricating, I'm reducing friction. So this reduces friction between the wheels and the skateboard, obviously not the ramp. And that means that less energy wasted as thermal energy of the surroundings, the thermal store of the surroundings, or you could say that more energy is usefully transferred. And therefore, that means since more energy is usefully transferred, it will go to the kinetic store. So more kinetic energy, which means faster speed. So there's more kinetic energy, which is equal to half mv squared. That will mean more speed since the mass of the person remains the same. Another question says, to heat the house, the boiler transfers 15 megajoules of, so this is the energy, and mega stands for the 10 to the power of 6. I will do a separate video on unit prefixes and rearranging and things like that again, to save a bit more time. Of energy in 10 minutes, calculate the power of the boiler, write any equation that you use. Now they started adding this probably because many people lose marks for not writing their equations and showing that how they substitute. I did say already that we have to use these numbers in joules and seconds, not in minutes. So 1 minute is equal to 60 seconds. So obviously 10 minutes, that means it's equal to 600 seconds. So my energy is 15 times 10 to the power of 6 joules. That's what this stands for. This is a unit prefix. Please revise them. T is 10 minutes, which is, we said already, 600 seconds. So power is energy divided by time. So I changed both of my units. I should probably give me a mark each, if not a mark 1 for each one, for both. A mark for the equation and then a mark for putting down the correct numbers in and getting the right answer for it. So please make sure you always list your values, make sure you write your equations and memorize your equations appropriately. In this question, it tells you to write down the equation that links energy transferred, power, and time. So you have 3 variables. How are they linked together? Well, you have to write it fully, but I'm just writing it like that for short time. And then the question says the power output of an immersion heater is 5,000 watts. Calculate the time taken. So I need to find this. So power is this much. Time taken is what I need to calculate. For the immersion heater to transfer 4,070,000 joules of energy. Give the unit. Okay, so my first task that will be to give the unit, because I know that time taken should be in seconds. Since I'm already given the watts and joules here, I don't need to convert any units like I did before. But I do know that power is energy over time, and I need to rearrange to make time the subject. Now time is at the bottom, so I need to bring it up to the top first and then make it the subject of a formula. So I'll do since I'm dividing it, I'll multiply both sides by t. T divided by t is 1. So now I need to get rid of power from next to it. Divide both sides by power. And you end up with energy over power. Now, you could have simply just flipped these 2 points here. I can explain it in another video. If you want me to make another video on this, just request it and I will do it. You can request it through Show My Homework if you want as well. So we have the energy, which is 4,070,000 divided by 5,000 watts. Just get rid of the zeros, and whatever number you get, you put in the equation. And these were a bit hard. These were rearranging. There was no substituting yet or anything. And I need to add also a question about efficiency in a second. Now you have figure 3 here. It shows a roller coaster. Now roller coaster questions are quite often used, and we will also see how we can attempt them. Now it says the roller coaster car is raised to a height of 40 meters in 35 seconds by an electric motor. The mass of the roller coaster and passengers is 550 kilograms. The motor has a power rating of 10,000 watts. So it's giving me so many information here, and I need to figure out how to calculate the efficiency. So all I'm trying to find out here is the efficiency. I know that efficiency, firstly, is the useful output. Now, this is a 5 marker. This is a high-end question. This is for those of you who are targeting to get something about above 7. So that's a useful output over the input. Now, where can I get my input? Well, I can get my input from here, because it tells me the motor has a power rating of 10,000 watts. It means that it tells you the motor tells you that I'm going to give you 10,000 joules of energy for every second. Remember, that is energy over time. So that means it's giving me 10,000 joules per second. Now, instead of using output energy, I will use output power and input power. And since energy and power are directly proportional, since power is energy over time, then that doesn't, and this is a fraction, it doesn't have units, so power divided by power, so watts divided by watts are no units, so efficiency doesn't have any units, it's a number or a percentage. Then I can use this equation as well. So it says the power rating is 10,000 watts. That's what my machine is given, my motor is given. And I want to find the efficiency. Now, I know that the motor that's operating the roller coaster took 35 seconds to raise it. Let's say this is my 40 meters. So it took the motor 35 seconds to raise it by 40 meters. It gives me the mass of the passengers and the roller coaster, as well as the gravitational field strength. It gives me the height. Now, if I wasn't sure about my energy transfers, which I should be at this point, now if it raises it, then it means it gains, the energy is being transferred to the gravitational potential store of the roller coaster and its passengers together. So if I'm assuming that here I had 0 joules of gravitational potential, then I know how much it gained. So was the energy, the useful output power, that's what I need to calculate, the useful output power. But to get the power, I need to first calculate how much energy was transferred to the useful gravitational potential store of the roller coaster and passengers together. And I know I can do that using this equation. So I'm going to find first the energy, which is 40 times 9.8 times the height, which is 40, oh, sorry, my bad, 550, the mass, and the, that sounded small as well, 40 kilograms, that's a very little for a roller coaster and the passengers. But yeah, the passenger's mass times the height. So this will give me the gravitational potential energy that the roller coaster with the passengers gained due to the motor. This means I have 215,600 joules of energy being transferred, but I know that this energy has been transferred in 35 seconds. So power is energy over time, which is 215,600 divided by 35 seconds, which should give us 6,160 joules, watts. So that's how much power was transferred usefully to the gravitational potential store. And now I can calculate my efficiency. So that was my useful energy divided by my, useful power divided by my input power, which gives us 0.6216, which is roughly 0.62, or if I want it as a percentage, is 62%, so just multiply it by 100. So there you go. That's just about the whole P1 topic. If you have any questions, don't feel shy to ask me.